Okay, that should be working. Should we get okay? Okay, you guys should be working on project 4 unless there's another class that's kicking your butt, right? Is there another class kicking your butt? All of them? So we're all. It's November. It's time for everybody to be falling behind in all their classes. Uh, that's the way it is. I got some questions from other people. I thought I had already said this, but maybe they didn't hear it on the recording. This S is equal to 0 is associated with this transition from state A to state C, not this transition. The transition from D over to state A is unconditional. That means whenever you hit state D, without looking at any inputs, the next state should be A. You're only in D for one clock cycle. Okay? There's an awful lot to do on this. There's an awful lot to do. Um, I would make it different, but I know that I have to test you on some of this stuff. Some of it's like even ABET stuff that I've said, we're going to make sure you guys know how to do this, and so I'm using different problems on the test to show that we are doing what ABET needs us to do. Now I put this out there to help. Now it's a little different. Okay, it has states numbered instead of states lettered. Who cares? It's the same thing, right? It's a symbol. I showed here one hot encoding. That's what you have to do on this particular thing here. It says use one hot encoding. Okay. It shows how to use inputs, and like going from state 2 to state 5, R is equal to 0 and S is equal to 0. So when I've got state 2 or state B, and I got both R and S is equal to 0, I go here, which is really state 5 or state E, whichever you want to call it. Okay, so you see how those are associated? So I've got this out here as an example so that if you're going through this, and you can ask questions on it, we can go through it a little bit today if you want, and it should help you get project 4 done, which is due Sunday evening, right? And I know you've got stuff due in other classes, so this one will take a little while. And if you're going to sit down and do it all at one time because of other stuff in other classes, so you're going to sit down and do it all at one time, get started early Sunday because it's going to take you most of the day. All right. Now, this says use this. It's only got 4 states. I do have 3 inputs though. It says develop a state table. This is a state table. This thing right here. Okay. I said it's an individual project. You can get help from others, but you gotta do all the work on your own. RS and T are the inputs. The outputs of the system are just the flip-flops. Well, in here, I do have outputs associated with the states. This would be, the way I've got it associated with the states, it would be just the flip-flop. So when I go into state 2, Z better be 0. Here's state 2, Z is a 0. Here's state 3, Z is a 0. Okay, state 4 and 5, Z is a 1. But on this one, I said the outputs of the system are just the outputs of the flip-flops. Well, that would be these right here. So instead of, and remember, the output's always associated with the current state. So instead of the output being 1 for Z, the output is 1, 0, 0, 0, 0 in this case, or 0, 1, 0, 0, 0 in this case. We don't have a Z. These are our outputs. Okay, so you don't really, and kind of, in other words, you don't really have any outputs to worry about. You just go to those states. Use one-hot encoding. This is one-hot encoding when there's only one flip-flop high at a time. Use negative edge trigger D flip-flops to implement the design. Well, this is because, and this kind of sucks, but you got to do it twice. Okay, so this first time, here's the D flip-flops. We know that if, okay, so we look at Q4, we see 0, 0 here, so it's always 0, so D4 is 0. Q3, it's always 0, same thing. Here, R is 0 and 1. S doesn't matter because S doesn't have anything coming out of state 1. There's R and there's R. And those are the only two transitions leaving state 1. R is 0 or R is 1. So here, finally, we get to 1, 0 for Q2, right? That's this one. R is 1, and let's see, we go to state B, which is this one. But here it's showing, for this particular one, we got 1, 0. That's the opposite of R. So I've got not R here. Okay. Here, this 0, 1 is the same as that. And this, I'm getting that by saying here, R is 1, I go to state 2. Here, R is 1, I go to state 2. That, just this part here, right? State B. Here, R is 0, I go to state 3. Here, R is 0, and here I'm going to state 3, which is C, right here. Okay, so that's where I'm getting these numbers. 2, or state B, is, I can call it either one, is 0, 0, 0, 1, 0. 0, 0, 0, 1, 0. State 3 is 0, 0, 1, 0, 0. Right there, same thing. So that's where I'm getting these numbers. Then, when I'm looking at how is R and these going to affect my inputs to the D flip-flop, here I see 2 zeros, so the input's always 0. Here the input's always 0. Here the input is 1, 0. That's the opposite of that, so I can find it right here. Here it's 0, 1. It's the same as that, and here it's always 0. Now, the one thing that you will find in one-hot encoding, almost every time it's either going to be 0 or it's going to be something to do with the inputs. This is the only place where it's 1. And that's because when I'm in state 3, I only go out one place, right? I only see one transition arrow coming out of state 3. The rest are coming into state 3. And it is unconditional. So, there's nothing here to do with the inputs. 0, 0, 0, 0, 1. I go back to state 1 or state A. And that's the only time I've got a 1, when there's only one unconditional transition here. So I should have something like that when I go from D to A, right? Same kind of thing, because there's no variable that's helping there. So this is unconditional. So I will have I don't know. I'll probably end up, if most of you guys would say this is state 0001 and 0010 0100 and 1000. I mean, that's the way you would probably do it. So when you're in D, the next state is A. So it's kind of like this one. If you're in D, the next state is A. So if A is 0001, again, you would have a 1 in this furthest column, just because there's only 1 here. Okay, what I think is well, I don't have the rest of the work done here. I've just got that, and then I've got the VHDL, and then I've got the output from you know, whatever my simulation was. But remember, when you go to do when you go to set up the what do you call it, the Carnot maps, you go by a column. When you're setting up the rest of this up, you're going by row. But when you're setting up the Carnot maps, you're going by column. Now, how many variables is it? It's a whole bunch, isn't it? So we got to find some way of reducing this in some form to be able to come up with this expression. The good thing is that it's 0 for everything. The other states we don't care about. So even if this was a 5 by 5 Carnot map, everything would be 0 or don't care except for this one. So the only input that matters here is always going to be 0, except for when we have Q1 and not R and not S. So that's a little different than we've done before. But I don't know how we're going to put a 5 by 5. You can do a 5 by 5 Carnot map. What you have to do is have like a 3 by 2, and then have no, you got to have 4 by 4. Let's say with Q3 through Q0, and then you end up with, is it 4 or 5 of them on top of each other. So then you got to kind of think in 3 dimensions, like one's on top of the other. It gets a little, that's for this. For what you're doing, there's only 4, thank goodness. Okay, so you only have 4 states. And that makes it a whole lot easier. This one, there's 5. So we're not going to worry about it. If it were 4, you would have these inputs, let's say the last 4. You'd have 0 at all the cells except for this one, where it'd be not R, not S. So it would be Q1, not R, not S. For this one, you would have Q1 and S, or Q4 and not R. Okay, I guess I could call up Word and write some of this down. Okay, so when you get this one for D4, damn, wouldn't you know it? The equation would be, you look only at this part and over here, and you've got a Q1 and not R, and this should be an and also. And then this one should be not S. So there's the equation in this case for R. For this one, you look at, when there's zeros, we don't care. If there are cells on a K map, we don't care about them when they're zeros. We only care when there's one. This one has two of them, here and here. So for D3, we would have S and Q1, or, so now I need to go back and put the parentheses around here. And I'm going to show you something here in a minute. It might be easier to do the VHDL first here, and that would be this one, Q4 and not R. Okay, so let's take a quick look. I've got these two. We can come back. Let's take a quick look at this. So I was just in, let me go back up here. I was in state B and said, when in state B, we go to this state when, maybe it's not as easy. You say if R is equal to 0 and S is equal to 0, then we go to this next state. I did the type, state type, a state type, and those are the 5 values. And then I said when we're in B, if R is equal to 0 and S is equal to 0, so we're looking here when we're in B, and R is equal to 0 and S is equal to 0, we go to state 5 or state E. And that shows this, and here shows the way the flip-flops would be. So I'm not sure which is going to be easier. I was beginning to think that it would be easier to do the VHDL first and then go back and from this take out the what these equations would be. I'm sorry, what these equations would be, but that may not help at all. I don't know. You might just have to look at these and do your best at trying to figure out what they are. For D2, that's a long one. It's going to be, you got to go back and say Q0 and not R, or Q3 and not S, or Q4 and R. And for this one, it's fairly easy. It's just this one. And then we got those. And then whenever we're in state D or we're state E, that we should see in the VHDL file, that when we're in state 4 or state 5, Z is also equal to 1. So that we show down here when Z is equal, or it's equal to 1 when we're in state E or state D. Else it's 0. You guys might have to start this before Thursday, so you can come in Thursday with questions, because I don't know if, I think I might even be making it more confusing right now, because you haven't looked over this yet, and you haven't really looked over this yet, and so it may be just making it more confusing. I don't know. We left off on these with, maybe it would be helpful to just go through these in a, in a more standard format that's that you can go back and look at. I'm trying to do this the best way I can, but when I went off that way, all of a sudden it didn't seem like that was the best way to do it. You guys are the ones that are sitting there listening to me, or maybe not. Maybe you're doing something else. Which seems like the better way of doing it. This example, we did the sequence detector. We were doing alternate design approaches, I believe, when we left off the other day. Yeah, I was showing you. Would this be better to go through this again to get you ready for Project 4 or not? I think the problem is you're in my class and one other one that's kicking your ass, and it's all coming down to the wire here, or at least that's what I'm hearing from DE. Okay, damn. I'm thinking it would be better to go back through this because there is some one-hot encoding in here, and then if I can come back and do maybe some other stuff. Okay, this Project 4 help file, it's just supposed to be an example of having been starting out with the state diagram, having some variable inputs, and then going to this state table or go to the VHDL. I hope it's helpful. It may or it may not be. I don't know. So remember, you got to ask questions before Saturday, or I'm gonna be going, damn. They're gonna have to figure it out. Okay. So you've got to do the one-hot encoding, use D flip-flops. You better be glad I did that. I could have said JK, and that just adds a whole new level. Then you got to come up with the test bench and the VHDL code and use the test bench again. And then the report, again, it can be real simple, but all the diagrams you put in there, you got to tell me what they are. Make it as simple as possible. If you start on this before you come to class Thursday or you come to lab on Friday, I'll answer whatever questions. I need to see that you've done some work, though. Otherwise, it won't make any sense. Just about like it's doing right now. Okay? So have something done, and I'll be glad to answer any questions you got. We were here the other day. We left off at choosing, I think we had started some of this, and we looked at the example that we had before where we had state the output Z, and I said using instead of having these as 0, 1, and 2, we can make those whatever we want. And so I decided to make these 0, 1, and 3. These, I mean, they're going to be zeros or ones because we're using flip-flops here, but you can make them whatever you want. If it's this could be 3 and this 2 and this 1 if that's what you wanted to do. It can be whatever you want. Because all this is supposed to do is keep track of what the current state is. That's all that's for. And so as long as this doesn't appear in 2 places, you're all right. That's just saying that 0 is A. We could say 3 is A, but then that would be the only one. Once you've assigned these, you've got to stick with them. This you don't assign. That's part of the problem. Like here where W was 1, W was 1, and we finally got down to state C. That was the definition in the problem. Okay, so then we, thank goodness here and on your other one, you're only going to have 4 states, so you're going to be able to have a small truth table. The worst you'll get is in the assignment. Since this is a I'm thinking I might have to take that other one away completely. It might mess you up. Since there's only 4 states, you're only going to have 4 state variables. So the worst you're going to have is a 4x4 K-map. That's the worst you're going to have. But you're going to have one for each D flip-flop, which would be, there would be 4 of them. Yeah. I'm sorry?
You said you will take that example away. Don't remove it.
Do you want me to or not?
No, I don't want.
Don't? I'm afraid that it would, that it might confuse you more. Okay. If you think it'll help, then I'll leave it up there. If it looks like it's starting to confuse you, just ignore it and ask me some questions. Now I know that there's another class or two that could be giving you guys a rough time right now, but if you can, between now and Thursday, try to at least start that project 4. How many of you have started it? Okay, and it's due Sunday, right? And the next one is really involved. That's why I'm giving you 4 weeks on that one. So you almost have to start this one before Thursday so that you'll have some questions. If you don't start it, you won't know what to ask me, and I won't know where you're having problems. And so then what did I say? I wasn't going to answer questions on Saturday or Sunday? Yeah, well, then you won't have any time to ask me any questions, will you? You'll be kind of, and the worst part of this, the reason I'm being so insistent about doing this is I know there's going to be questions on the final exam where you need to know this. Okay? I want you to do well on the final exam too. But I can't help you unless you try, unless you start it. Okay. Here, I showed the Carnot maps. Again, this didn't have anything to do with having one hot encoding. That would make your project a whole lot easier if this wasn't one hot encoding, because then you would only have 2 state variables for those 4. You guys have started it, so you're using one hot encoding. Yeah. That makes it a little bit more difficult, but let's stick with that. There's already people trying it. Okay, so this one, since we've only got 2 variables, we just got a 2x2 K-map here. And this one, it had to be that. Then I decided to simplify it by pulling W out and having this. It was just because I was going to be drawing this schematic. This one, we got WWW and I don't care. So we can circle this whole thing, and it says then that D0 is just W. That was nice to have that. Looking at these again, this should have been 10 because that's associated with the present state. 1 0 associated with the present state, and 1 1 associated back here. But as you can see, if it's 0 0 1, this is 0 0 1, it's the same as y1. Okay, you could make it more difficult if you want. It wouldn't hurt anything. You could say that z was equal to, you know, let's say it's only going 1 here, so you could say it was equal to y1 and y0. It's a little bit more, I mean, in this case, it's just one more variable, so it's not that big of a deal. But in some, it could make it more difficult. But this one, when we've got a 1 here, and this is the case, we can say it's y1 or 1 and y0. Or you can go back and try to look at this and say, is there a pattern here that looks like this pattern over here? And if this was 0 0 1, that 0 0 1 looks just like y1. So that's how I chose it. It was just through observation. Okay, so there was the new schematic. You can look at the last set of slides if you want to and see how much different they were. This, for some of the guys in the DE class, I gotta say this real quick. In your report for 3, you were looking at this sample report, and a lot of the folks, man, it looked real close to this. I dared not read it too carefully, because if it was too close to the same thing, I would have been turning some things in. But then I started seeing these. That worries me when I see these, because I know we don't have them anymore. And so when these show up in your report, I'm like trying to read real carefully here. Is this what you use to come up with your VHDL test bench, or are you trying to tell me that this is your VHDL test bench? Because you can't be using this. They don't use them anymore. So I saw that in a number. You guys just be careful. If these are appearing in your project, make sure you're telling me you just use this to figure out what the timing was for this. Otherwise, this stuff shouldn't be there. A lot of these images looked real close on some of the DEs, and I sent out a lot of warnings. And be happy with that, because normally I don't send out warnings. I just contact the dean of students. Okay, so we have these. We don't have them anymore. But this one, another thing you've got to watch out for, what I'm seeing in some of these reports, is these resets. If you've got a clear here and there's no bubble, as long as this symbol, or as long as this is high, it's going to keep this Q at 0. Now here I put an inverter in for both of them, so I have to have reset low, then that'll make sure this is high. Okay, so that's like putting a bubble on both of those. But I could have reset go low, and then this thing is operational. I had it go high at the very beginning, so it cleared it out and we had a place to start. I'm seeing some of these results where the output and the output here is just a flat line. And then I look up at the reset, and the problem is that reset's holding it low the whole time, or holding it high the whole time. Watch out for that. It's your whole test bench isn't doing you any good if you're using this one line to keep it high or low the whole time. you do have to have it at the beginning so that Xilinx will know what the initial output of these are, especially with J, K, and T flip-flops that are always um, dependent on what the previous state was. Uh, if you don't tell it at the very beginning what the current state is, then it doesn't know throughout the whole rest of the timing simulation. Okay, one hot encoding. Let's go through this one. Maybe it would have been helpful if there were 4 like your project, but I've only got 3 states. So I've got 3 state variables. That means I've got 3 flip-flops. If it's a more machine, because I've got the states associated with, or I'm sorry, the output associated with the states, not with the transitions. Okay, so state A, I've got 1, 0, 0, state B, 0, 1, 0, state C, 0, 0, 1. These don't matter as long as they're all different. If you can't have 2 of these the same, but what they are doesn't matter as long as they're all different. And because it's one hot encoding, there has to be as many state variables as there are states. All right. So for this one, when we're in state A, if W is a 0, we just stay in state A, 1, 0, 0. Looks like state A. If W is a 1, we go to state B. That's 0, 1, 0 right here. So typically we got to fill out this part of the table first, so we may as well go down to B here and say when we're in state B, if W is a 0, we go back to state A. That's state A. And if W is a 1, we go to state C. So this looks like state C, right? And then here on state C, if W is a 0, we go back to state A. Again, that's state A. And if W is a 1, then we stay in state C. So we stay here. Okay, so once we have these 4 figured out, now we're working in columns. So here we're saying the input to D2, I got to look at what my next state's going to be, because this is going to be the current state of 1 for D2 and a 0 for, I'm sorry, for the output Q2. I called it Y2 over here. And Y1 and Y0 are both going to be zeros. That's the current state, but this is what my next state has to be. And the next state for this one, it's nice on D flip-flops for your next state, you put what's going to be there, or what you want for the next state. So here, if the input 0, I want the next state to be 1. If the inputs, or if W is a 1, I want the next state to be 0. Well, that looks like not W. So that's what I have to connect to the input of this D flip-flop. Here, on this second one, 0 on 1, and this is 0 on 1, so D1 is exactly what the input W is. And on this third one, it's real nice for us because it's 0 no matter what, so we just put a 0 at the input there. On the second one, our inputs again 0, 1. Again, the way this worked out is for which state we're going to go to next. We got 1, 0, which is not W, For the middle ones, we got 0 no matter what. And for this one, it's W. And the same thing here. We got 1 0, which is not W, 2 zeros, and then 0 1 and 0 1. They're the same. So if now's a good time for questions on how I got these, if you don't understand that. Sometimes the question is, I don't understand what you just did. Could you do it again? Sometimes the question is uh, a little bit more direct. But if you have a question, even if it's, can you show me that again? I can do that.
So, like our project, we have 4 states. For the present state, and we put just zeros in front of all that, and that would be a 4-state machine. I mean, because they have a different values like 0 1 0 0 0 0 1 0.
And so you'll have 4 states, so there will be 4 rows now.
Yeah.
Okay, so A, B, C, and D. Mm-hmm. That's what I've got. Okay. You can choose any one of those to have. You're going to have 4 state variables, so you might want to call them Q because that's what we're used to the output of the flip-flops being instead of Y. So you might have Q3, Q2, Q1, Q0. You're going to have 4 of them. Okay? And so, yeah, on this first one, you could have 0, 1, 0, 0. Here you could have 0, 0, 1, 0. Here you could have 0, 0, 0, 1. But on that fourth one, that Q3 would have to be the 1.
And everything else is 0. And then the input W would be those 3 inputs, R, S, and T, right?
R, S, and T, yeah. And I made that a little complex because there's 3 input variables. Don't let that bother you. Okay, you can. I know that's easy for me to say, but just look at these are ANDed. When I've got them like this, S equals 1, comma T equals 1. That's an AND situation. Both of those have to be AND. This is too, actually. I say OR when it is OR. So this one says if R is equal to 0 and T equals 0, or if they're both equal to 1. This one just says R is 1. This one says R is 1 and T is 0. You'll start, as you're putting these into the table, you'll start seeing that these basically got to be different or it might take you to the wrong state. So, yes, you have R, S, and T. And for every one of them, for some of them, like this one, this doesn't have R associated with it. It doesn't have R associated with it there. And it doesn't have R associated with it here. So the 3 transitions leaving A don't involve R at all. So R is going to be don't care. Okay? So when you look at B and look at the transitions leaving B, it's this one and this one. And it's just R. So S and T don't matter. Those are going to be don't cares. For C, we got this transition leaving, this transition leaving, and this transition leaving. And they're both R and T. Nothing to do with S. So S is going to be don't care. Okay? This one's going to be if R is 1 and T is 0, we go to A. This one's going to be if R is 0, T is 0, or if R is 1 and T is 1, we go to B. And this one's going to be if R is 0 and T is 1, we go to D. Whenever we get to D, we immediately go to A the next time. It doesn't, all those variables say I don't care at that one. Okay? So this is very similar if we put on one row here and add one state variable, which means we add one flip-flop to the mess. And it's not, this here should help maybe better than the other one. If you're looking at that other example and you start going, oh damn, this is just screwing me up, throw it out. Don't look at it anymore. Okay? All right. So we start filling in our Carnot maps. I know it's a 2 by 1 because I got 3 state variables here. So I know that even though I'm not showing the other states, I know there's a 0. I've got 1 here. I've got 2 here. There's a 3. This is 4. And then there's 5, 6, and 7. So the 0, 3, 5, 6, and 7 are all don't cares. If you want to throw them in there, you can just to see them, but it might complicate things. So I don't know what you want to do. But I know that here, in every one of these situations, these are all don't care. Now here I look at these 3, and for this cell, cell 4, cell 2, and cell 1, they're all not W. So I got not W. And since these don't care, then I can circle the whole thing together and say that D2 is equal to not W. Okay, here I got 2 zeros. Which one am I looking at? I accidentally skipped D1, sorry. Here I've got the 2 zeros for cells 1 and 2, so 0 doesn't care and 3 doesn't care. 4 is a W, and then 5, 6, and 7 don't care. So these zeros, we throw those out, and these we look at. This would normally, in a normal map like I've been doing all semester, that would have been an A. But I don't want to use A because I've got my states labeled A, B, and C. And if I said these were A, B, and C, you'd be going, well, is that this A equal to that A? And no, it's not. So I had to do something different. But then where would we normally have A up here? If we had A, B, and C for these 3 variables, we would have A as the most significant and C as the least significant. So Y0 are these 2 rows. This is Y0 not, and this is Y0. These 2 are Y1, and these 2 are Y2. That's why this is Y2. Does that make sense? I just want you, I mean, normally we call this A, these 2 B, and this row C, but I can't do that because it's not the same as those states. Next one is D0. For state 4, I got a 0. States 5, 6, and 7, I don't care. And then for state 1 and 2, I've got a W, and these 2 we don't care about. So this Y2 not, this would be as if these 2 columns were A, these 2 columns would have been A not. This would have been in position A, this most significant column, so that's Y2. That's how I'm getting Y2 here. I should have, when I made these slides up, I should have made this so that it was clear this is Y2 and Y1, and down here is Y0, but I didn't do it. So we're stuck with these older things that that don't have that. Maybe I need to go back and put them in, but it's not going to help y'all this semester. Then I had to find something that looked at, remember, I can't say it enough, that the output is associated with the current state, but you can see that here in this diagram. The current state and the output are associated together. So when I look at this output of 0, 0, 1, I'm looking over here at the current state. Does anything pop out as being similar to that? And Y0 does. So I said our output was just the same as Y0. So here's my new set of equations, and I don't know if I didn't, I'm sorry, I did not come up with the new circuit, but I think you can understand how to hook up that circuit. You have 3 flip-flops. One has these 2 for the input, one has these 2 for the input, third one has this, and the output's taken off of the output from this flip-flop. And that's our output Z. Okay. What we've been doing is more machines. So this blue line that I had at the beginning was not there, but in a Mealy machine it is. And most of you are not going to use a Mealy machine. Some of you are. It might make more sense to you to use a Mealy machine. But I just noticed there's not any real noise coming from over there today, is there? Huh?
Do you like it?
I can't hear anything. Can you hear anything? Okay, that's good, isn't it? Okay, do you want to go through this Mealy machine or not? Will that confuse the issue?
You can explain. That's fine.
I can't. Okay. Again, on the Mealy machine, the output logic is associated with both the registers or the current state of the machine and whatever the input is. So I can use both of them. Here's where we're looking at the input. So in a way, the output is based on the transitions that are taking place, and that's why they look like this. Here, when we're going from state A to B, W had to be a 1 and Z was a 0, right? We didn't have 2 1s on W, so Z was a 0. Here we would have 2 1s on W, so Z would become 1. But here, if W went low again, then Z would have to go low. And over here, we would stay in A if W was 0, and that would keep Z low. Okay, so it's the same. It looks a little different just because our output's associated with transitions instead of with states. So it does become a simpler machine. This is our new state table. Now we do have to have 2 variables here because Z is associated with this and the current state, not just the current state. So, and you can tell real quick you're working with a Mealy machine when you have this kind of a situation. Okay. So when you've got that, we can say that Z is equal to W and Y0. Because that's Z, or I'm sorry, Y0 and W, or when Z is 1, if this is a 0 or that's a 0, then Z becomes a 0. And that was a simplified. That there is why people like Mealy machines. They're so much simpler. But remember, it wasn't many years ago that we didn't have things like Xilinx and VHDL and Verilog that people were using constantly. You know, it wasn't too many years ago that people were still doing all their design uh, with the state tables and hooking them up with flip-flops and stuff like that in the lab. They didn't have Xilinx or Verilog to work with. Or I'm sorry, the other one is Quartus, Xilinx or Quartus. And Xilinx, we can use Verilog or VHDL. It doesn't matter. So this became very important that this was so much simpler. So there was a lot of faculty that would say, you got to do a Mealy machine. You got to do a Mealy machine because it's a much simpler machine than what we have here. But here it doesn't really matter. I personally think that the VHDL is much simpler than the schematics here. I did start this the other day. I think I already said a little bit about this. You can create a new type of variable by using the keyword type. And here I called it state type. Well, that just the variable name that I chose may have thrown in some extra confusion because I've got type, state type. It's like I could have called it something different, but I didn't. So I've got type, state type, and then the keyword is. And here in the parentheses, I'm putting the values that state type can take. They can only take on A, B, or C, period. Okay? Now that's like an integer or a double or a character or something like that. I've created a new type. In C, this would have been a struct, right? I would have created a new type of variable by having a structure. Okay, here I'm creating a signal. Do you remember what a signal is? A signal is a set of wires or something inside the entity that never go to the input or the output. We can't ever touch them. We can't ever touch a pin that says this is part of that signal. So I've created, and the other thing about them that's real nice is they're never defined as an input or an output. They can have data flowing either way on them. So here I've got a signal that I'm calling Y and saying it's of type, state type, not standard logic or something like that. It's a state type. So Y is going to only have 3 possible values, A, B, and C. That's because they're state types. So my process, and remember I'm going back to this to come up with this this VHDL. So the process is if clock or the reset pin change, then I begin. If the reset 0, then I start in state A. Now I just do that. Let's go all the way back to here because I arbitrarily chose reset here. I could have chosen it to be somewhere else, but I chose it to be there. So if reset equals 0, then the state is going to be assigned state A. That's what that says. there's only a single quote here because I only have a single variable value, 0 or 1, right? If it was more than 1, then I would have double quotes. Okay, here. So I've got if reset equals 0, then this, else if we have a transition on the clock, and this is a positive clock. Clock event and clock goes high. Then my case is centered on the type of state it is. So when I'm in state A, if W is a 0, I stay in state A. Else, if the state is or if it's not a 0, it would have to be a 1, then I go to state B, and then I end that if. Okay, and this, I guess, is associated with the Moore machine because it also has a state C here. But then when I'm in state B, if W was a 0, then I go back to state A, else I go to state C because it would have to be, Y would have to be a 1. And then I end that if. And then I'm in C. If I'm in C, if W is a 0, then I go to A. Otherwise, I stay in C. To me, that is so easy to look at this and use that VHDL to come up with those cases. But that was this, not that one, because I have states A, B, and C. This one's only got states A and B. Okay. Now this, when I end the process, I can finally say that Z, and it's not shown here, but Z is shown on the entity. It's the output. The input is W, right? So I'm not showing W anywhere but in here. Those are in the input or in the entity. But Z is assigned to 1 when I'm in state C, else it's a 0. But that takes place outside of the process because Z is an output only. I can't ever say that Z is equal to not Z. I think you guys are finding that out on your flip-flops, right? You can't say something like Z is equal or Q is equal to not Q. Won't work because they're both Q is either an input or an output, and if it's an input, it can only appear on one side of that assignment statement, and if it's an output, it can only appear on the other side of the output statement or the assignment statement. So you need signals to be able to make those input or output assignments, and then at the end of the process, you can make assignments to the outputs. Okay, so this goes through and gives some examples of this. Now, I also put in here, you can just totally ignore this if you want. I got this process out of a book, and or this one, I'm sorry. I got this out of a book for the Mealy machine, and this is a very well-known book. And got this out of the milling machine, and when I tried it, it didn't work. And I know I checked a dozen times to make sure I had this typed in right. It just didn't work. So there was something wrong with this code. And since I don't really like Mealy all that much, I never went in and looked at it too close. So I put it back to C, put it back in the Moore machine, and it worked out a little bit better. Maybe I did fix it. I think this one worked. Anyway, okay. Questions before you get out there and start going through all this stuff? Are you ready to start on project 4? Damn, I wish you guys had started already. We would have been having some better questions today. Okay.
Will the lab be open this afternoon?
I can open it on my way back up to my office. Okay, I can do it. But remember, do you guys know what our wait a minute. Okay. That's it for today, right? All right.